So good morning. We had stopped in the last session by floating this numerical, which involved designing a UJT-based triggering circuit. So in order to solve this numerical, we need to revise this design equations. So we have 7 design equations which are written here, and using them with direct substitution, we can solve this numerical. Yeah. So we have our UJT triggering circuit. So the important design components which will decide the pulse width and the oscillator's output frequency available as voltage V0 across RB1 will be the potentiometer R, capacitor C, RB2 and RB1. So which are the things which are given in the circuit? Given VBB equal to 10 volts, we have eta intrinsic standoff ratio as 0.51, the pulse width given is Tp equal to 50 microseconds and frequency of pulses is 60 hertz. C is to be assumed as 0.5 microfarads. Another important parameters are valley voltage is 3.5 volt, the valley point current is 10 milliamperes and peak point current is 10 microamperes. Okay, so the unknowns are R is unknown, RB2 is unknown and RB1 is also unknown. At the same time, the maximum allowable value of R and minimum expected value of R is also unknown. These are the unknowns here. Fine. So we can find out RB2 from equation number 7 here. It's 10,000 upon eta into VBB, which is equal to 10,000 upon 0.51 into 10. VBB is 30 volts. I'm very sorry. So 653.6. So now coming to the value of R. So so from equation number 7, equation number 6. Six T is equal to RC into natural logarithm of VBB on okay, which is also equal to 1 upon F equal to 1 upon 60 Hertz. Vp is Vd plus eta VBB, which is equal to 0.5 and capital T comes out to be 0.0167 seconds. So we have 0.0167 equal to R. C is 0.5 microfarad. Natural logarithm of 30 upon 30 minus 15.8. equal to r into 5 into 10 raised to minus 7 natural logarithm of 0.748. Zero zero 447. Value of R comes out to be 44.7 kilo ohms. Now we can go on to find out the values of R min and R max. From equation number 4 and 5. R max should be less than equal to VBB minus VP by P. Now we are left with RB1. So from equation number 3, pulse width given is 50 microseconds. Okay. This is how you solve this numerical. So I hope all of you have got an idea about how to solve numericals like this. Dynamic turn on, dynamic turn off characters of an SCR. So before we start discussing about the actual topic, let us clear some basic things about this topic. First thing, as we told that SCR Why only SCR? Okay. That semiconductor devices when used in power electronic systems act as switches and connect or disconnect the load from the source. Okay, this we have told before and I'm repeating it today, that semiconductor devices when used in power electronic systems act as switches and connect or disconnect the load from the source. Okay, all of us being in third year, we know that a switch has only two states, that is on or off. That means a switch transitions between two states let us assume that first it is off. Transitions between two states, if it is off it goes to on state, if it is on it goes to off state. So the switch transitions between two states, on and off. Now another important thing to understand here is that when semiconductor device is used as a switch, it takes a finite non-zero time to switch between the states. Between these states. Okay. Now we come to the important point, that the voltage comma current across or through a switch. Okay, the point is, what are the voltages and the currents across and through a switch when it is in on state and when it is in off state. Okay, yeah, so we have the switch here. It is in off state or it is in on state. Okay. Now voltage across the switch. Current through the switch. Okay. So now students, I want to have answers from your side that we have a switch and the switch is in off state. What will be the voltage across the switch and what will be the current through the switch when the switch is in off state? Yes. So what is the voltage across the switch in off condition? What is the current through the switch in off condition? Yes.
So voltage will be equal
Okay. So voltage across the switch in off condition will be equal to?
V in.
Correct. Right. So it will be V in. What will be the current through the switch in off condition?
Zero.
It's zero.
Good. Okay. So now the switch is in closed condition. Now the switch is closed. So what is the voltage across the switch and current through the switch?
Voltage will be zero.
Okay. Voltage will be zero. Current through the switch? Suppose the load is Z. Then
IL.
now the value of the load is Z ohms. So what will be the current through the load when the switch is closed?
5 VA.
Hmm? Yes.
Pm sin omega.
No, but have I specified that V in is a sinusoidal source?
No, sir.
V in
Yeah.
is
V in? Yes. What will be the value of ISW when the switch is closed?
Okay.
Yes?
P in upon Z.
Yeah. I asked twice because I heard V in into Z. So it is V in by Z, correct. V in by Z, okay. So now students, the switch is transitioning from off condition to on condition. So when the switch goes from off condition to on condition, the voltage across the switch, it changes from V in volts to 0 volts, and the current, it changes from 0 to another non-zero value V in upon Z. But students understand that this is not a mechanical switch, this is a semiconductor switch. So a lot of semiconductor mechanisms occur within the semiconductor device structure, so that the semiconductor device, it now acts as a closed switch when it was acting as an open switch before some time. So I repeat that whenever a semiconductor device is used as a switch and it transitions from off state to on state, many semiconductor mechanisms occur within the device's structure so that it goes from off to on condition. That is what is the topic of discussion today. And understand one thing, that when we say that the switch goes from off to on and on to off in a finite amount of time, so we have to write a comment here that off to on is called as turn on time, which is not equal to 0. Similarly, when I have a transition of the device from on state to off state, I have another time associated which is called as turn off time, which is again not equal to 0. Understand one thing, that is why the transition from V in to 0 or 0 back to V in, or the transition from 0 to V in by Z or from V in by Z to 0 will all take non-zero times. Getting me, na? Yes. So now our topic starts here. Dynamic turn on. Yeah. So first point here, we consider the switching of an SCR from off to on state. In other words, it is from forward blocking condition to forward conduction state. Okay, FB to FC. So FB stands for forward blocking and FC stands for forward conduction. Okay. Second point, this transition takes a small non-zero time. Third, SCR is attempted to be turned on through an appropriate gate drive. Okay, so we are not going to have an SCR latch with VAK greater than breakover voltage, but we want to fire it, we want to latch it at an anode to cathode potential much lesser than the breakover voltage rating of the SCR. Okay, fourth important point is that the turn on process of an SCR is complex and divided into 3 distinct periods. Now this is technical, not periods, 3 distinct intervals, namely delay time, rise time and spread time. Delay time, that is TD. Second is rise time, TR, and third is the spread time, TS. Okay, so these 3 intervals comprise our T on. So we can say the turn on time of an SCR is equal to delay time added to rise time added to spread time. Now using waveforms, we can actually explain that what is delay time, what is rise time, what is spread time. But before we do that, we can actually define these intervals: delay time, rise time and spread time. So based on the definitions, we can very clearly draw the relevant waveforms. So let us define them. Delay time, it is the time interval between now please understand every word has been very carefully chosen, so please listen and understand carefully. It is a time interval between the instant at which the gate current Ig reaches 90% of its final value and the instant at which the anode current reaches 10% of its final value and the instant at which the anode current or device current reaches 10% of its final value. Okay, let us highlight these things, they are very important. Okay, so it is a time interval between the instant at which Ig reaches 90% of its final value and the instant at which Ia reaches 10% of its final value, and it is the time interval between these two instants. So we can basically say that the delay time is nothing but it is the time interval between these two, that is when the gate current reaches 90% of its final value and the anode current reaches 10% of its final value. So let us assume that the final values of gate current and anode current are Ig and Ia respectively. So we can say it is a time interval between the instant at which the gate current reaches 90% of its final value and the instant at which the anode current reaches 10% of its final value. Now we define the second interval, that is rise time. TR. So you know that in electronics, rise time and fall time are defined as a very standard thing. Usually rise time means the time taken for any parameter to go from 10% to 90% of its value. That is usually termed as rise time. The time taken by any parameter to fall from 90% to 10% of its initial value is called as fall time. Same definitions apply here also. So rise time means it is the time interval between following instants. It is a time interval between the following time instants, that is instant at which IA reaches okay. So this time interval between the following time instants, the instant at which the anode current is 10% of its final value and the anode current is 90% of its final value. Or it is also defined in one more way, that is the instant at which VAK is zero point 0.9 times of its initial value VAK and VAK is 0.1 times VAK. Okay, like that. So we can say that the rise time is nothing but it is the delta T between 10% of anode current and 90% of anode current, or also the delta T between 90% of VAK and 10% of VAK. Okay, this is nothing but the device is going from forward blocking state to forward conduction state. Okay, now one important technical detail is the rise time is inversely proportional to the magnitude of gate current. Okay, so we can say it is inversely proportional to magnitude of gate current. Okay, one more fact which is associated with the rise time is that the turn on losses are highest. Okay, so the turn on losses are highest due to non-zero values of both anode current and anode to cathode voltage or device drop. Okay, and third is called as a spread time. It is time required for the SCR drop VAK to drop from 10% of its initial value to the on state drop of an SCR. On state drop of SCR, which is 1 to 1.5 volts. Okay, so it's the time required for SCR drop VAK to drop from 10% of its initial value to 1 to 1.5 volts. Okay, and here after the spread time, the anode current IA attains a steady state value So when we say steady state value, understand it is nothing but V in upon Z, which we are talking about here. So V in upon Z is attained after the turn on time, or specifically after the spread time interval in the turn on process. V in upon Z. Okay. So we can say that after TS, VAK is equal to 1 volt to 1.5 volt, and the anode current has stabilized to V in upon Z value. Okay. So as we said before, again we will mention this, the turn on time. So thus T on is an algebraic sum of delay time, rise time and spread time, and is typically somewhere from 1 microseconds to 4 microseconds. Okay. and the width of firing pulse is typically kept 20 microseconds to 100 microseconds to ensure turn on. Ensure turn on. This is my gate current IG. Anode current IA. Device drop VAK. This is my power loss P. Okay, so we have only few minutes, but at least we can put the markers here. So this dotted line represents the steady state value of the currents IG and IA. This is the steady state value V in by Z. There will be a level corresponding to on-state voltage drop of an SCR, that is 1 to 1.5 volts. Let us assume it is 1 volts. And then we have 0.9 times IG, 90%, 10%. 90%, 10%. 0.9, 0.1 and V on. So we will develop these waveforms in the next session, that is tomorrow. So all this definition will be better appreciated then. Anybody has any questions they can ask? Any questions? Anything anybody wants to add?